Hello, and welcome to tonight's Space Sleep Story. If you appreciate what we do here, please like or subscribe for future relaxing nighttime space journeys. Tonight, we embark on a journey through the cosmic census of worlds beyond our solar system. Over 5,600 confirmed exoplanets orbiting distant stars, with thousands more awaiting confirmation. So settle into your most comfortable position, close your eyes, and prepare for a voyage through the galaxy of worlds. Before we begin, let us prepare your body and mind with gentle breathing. Take a slow, deep breath with me now. Inhale gently for 4 counts. Hold the peace. Exhale for 6. Feel your body releasing into stillness. Each breath brings you closer to complete relaxation. Let the day's thoughts drift away like clouds dissolving into evening sky. Another gentle breath as we continue our preparation. This time, notice how your chest rises and falls with natural rhythm, like waves lapping against cosmic shores. Let my voice be your guide. Hold this peaceful moment. Feel the stress of the day leaving your body. With each breath, you release a little more into relaxation, preparing for our journey among countless worlds. For thousands of years, humans observed stars as distant points of light. We knew the sun was a star by the 1600s. Philosophers like Giordano Bruno speculated in 1584 that stars might harbor planets. But we couldn't detect them. Planets don't emit their own light, except young, massive ones glowing from formation heat. They reflect starlight, billions to trillions of times dimmer than their parent stars. Detecting a planet next to a star is like finding a firefly next to a searchlight from thousands of kilometers away. Then came October 6th, 1995. Swiss astronomers Michel Mayor and Didier Queloz detected the first planet around a sun-like star using the radial velocity method at Haute-Provence Observatory. 51 Pegasi b. A hot Jupiter weighing 0.47 Jupiter masses orbiting every 4.2 days. The discovery challenged every planetary formation theory. Conventional models couldn't explain gas giants forming so close to stars. But rapid confirmations validated the detection. The exoplanet era had begun. Michel Mayor recalled the moment. We knew immediately it was something extraordinary. A planet with orbital period of 4.2 days meant it orbited closer than Mercury to our Sun. At first, we thought we'd made a mistake, checked everything multiple times. But data was clear. We'd discovered first extrasolar planet, and it was nothing like we expected. That's science. Nature surprises you. The discovery earned Mayor and Queloz the 2019 Nobel Prize in Physics. Following that first detection, the floodgates opened. 1999 brought discovery of first multi-planet system Upsilon Andromedae, with 3 planets detected by Geoffrey Marcy and Paul Butler. November 1999, first transiting exoplanet, HD 209458b, confirmed by David Charbonneau and Gregory Henry. The transit observation validated radial velocity detection and enabled atmospheric studies via transmission spectroscopy, demonstrating that photometric transit methods' viability for finding worlds that cross in front of their stars from Earth's perspective. But the true revolution came March 7th, 2009, with NASA's Kepler Space Telescope launch. A $600 million mission designed to determine frequency of Earth-sized planets in habitable zones. Kepler continuously monitored 150,000 stars in the Cygnus Lyra region until 2013. Then the K2 extended mission from 2014 to 2018 observed different sky regions. William Barucki, Kepler's principal investigator, had proposed the mission 5 times over 17 years before NASA approved it. Persistence paid off spectacularly. Kepler discovered 2,662 confirmed exoplanets. Statistical analysis of Kepler data suggested nearly every star hosts at least one planet. Think about that profound realization. When you look at the night sky, you're seeing not just stars, but planetary systems. Most with multiple worlds, some with planets in habitable zones, perhaps a few harboring life. Our galaxy contains approximately 100 to 400 billion stars. Extrapolation suggests 100 to 200 billion planets. We inhabit a galaxy of worlds. As of 2026, over 5,600 exoplanets confirmed in approximately 4,100 planetary systems. 900+ systems containing multiple planets. Exponential growth from 1 in 1995 to thousands today demonstrates detection technology maturation. The closest confirmed exoplanet, Proxima Centauri b, orbits the nearest star to our Sun at 4.24 light-years distance. A super-Earth with minimum mass 1.27 Earth masses in the habitable zone. Completes its orbit every 11.2 days. Our nearest potential neighbor. The diversity of discovered worlds challenges everything we thought we knew. Orbital period extremes span incredible ranges. Shortest confirmed orbital period, K2 137b, completes orbit in 4.3 hours. Planet surface reaches 2,000+ Kelvin, likely vaporizing. The longest period, Fomalhaut b, orbits approximately 2,000 years at 115 astronomical unit distance. Comparable to scattered disk objects in our solar system. From hours to millennia, planets orbit in timeframes our ancestors never imagined. The universe is endlessly creative. How do we find these invisible worlds across vast cosmic distances? Several ingenious detection methods reveal planets we cannot directly see. Transit photometry discovers 77% of confirmed exoplanets. When a planet passes between its star and Earth, it blocks a tiny fraction of starlight, causing detectable dimming. A Jupiter-sized planet transiting a Sun-like star dims light approximately 1%, easily detected. An Earth-sized planet blocks only 0.01%. Challenging but achievable with space telescopes like Kepler and TESS. We watch stars blink. Radial velocity, or Doppler method, discovered 19% of confirmed exoplanets. A planet's gravity causes its star to wobble, moving slightly toward or away from Earth. The stellar spectrum shifts blue when approaching, or red when receding, by detectable amounts. A Jupiter-mass planet at 1 astronomical unit induces approximately 12 meters per second stellar velocity variation, like jogging speed. An Earth-mass planet causes 0.09 meters per second wobble, barely faster than a snail. Current instruments push towards centimeter per second precision. We detect stellar dances. Gravitational microlensing discovers approximately 1% of exoplanets, but finds worlds other methods cannot. When a foreground star passes between Earth and background star, foreground star's gravity bends light from background star. If foreground star hosts a planet, planet's gravity creates additional brief brightening signature in the light curve. This method discovers planets at large distances, thousands of light years away, and cold planets far from stars undetectable by transit or radial velocity methods. Nancy Grace Roman Space Telescope launching 2027 will find thousands via microlensing. Gravity becomes our lens. Direct imaging discovers approximately 1.5% of exoplanets. Blocking a star's light with a coronagraph or star shade reveals faint planetary reflections or emissions. Requires large planets far from bright stars, typically young, massive planets still cooling from formation, self-luminous from residual heat. Current technology images planets 100 to 1,000 times dimmer than their stars, separated by greater than 0.5 arcseconds. Future telescopes, like NASA's Habitable Worlds Observatory, planned for the 2040s, will achieve 10 billion to 1 contrast ratios, directly glimpsing other worlds. Perhaps most exciting, atmospheric spectroscopy during transits reveals planetary compositions. Starlight filtering through a planet's atmosphere during transit shows absorption lines. Specific molecules absorb characteristic wavelengths. Water vapor, methane, carbon dioxide, sodium create distinct signatures. James Webb Space Telescope detected carbon dioxide in WASP-39b's atmosphere in September 2022, the first definitive exoplanet carbon dioxide detection. Though WASP-39b is a hot Jupiter at 870 degrees Celsius, the detection demonstrates Webb's capability to characterize temperate rocky planet atmospheres. We can taste alien air across light years. The discovered planets reveal unexpected diversity. Hot Jupiters, gas giants orbiting very close to stars at 0.02 to 0.1 astronomical units inside Mercury's orbit in our system. Temperatures range from 1,000 to 2,500 Kelvin. orbital periods of 1 to 10 days. Tidally locked with same face always toward star. 51 Pegasi b, the first detected around a sun-like star, exemplifies this class, with mass 0.47 Jupiter masses orbiting every 4.2 days. These worlds shouldn't exist, according to original formation theories. Yet they orbit by the hundreds. Super-Earths. Planets with mass 2 to 10 Earth masses have no analog in our solar system. Earth is our largest terrestrial planet. Uranus, our smallest ice giant, weighs 14.5 Earth masses. Super-Earths fall in between, creating classification mystery. Are they rocky super-terrestrials, water worlds with deep oceans, or mini-Neptunes with thick hydrogen atmospheres? We don't yet know. Approximately 30% of Sun-like stars host super-Earths, based on Kepler statistics. The most common planet type in our galaxy is absent from our home system, making Earth perhaps less typical than we assumed. Mini-Neptunes. Planets 10 to 20 Earth masses with substantial hydrogen-helium atmospheres over rocky or icy cores. Most common planet type in galaxy based on Kepler statistics. Yet our solar system contains none. This absence raises fundamental questions about planetary formation conditions and migration patterns. Why does our system lack the galaxy's most common world type? Did Jupiter's formation timing prevent mini-Neptune formation in inner solar system? Understanding this absence helps reveal our system's uniqueness or typicality. Every missing world tells a story. Ultra-short period planets orbit in less than 24 hours, some as brief as 4 to 8 hours. Survival at such proximity, 0.01 to 0.02 astronomical units from stars, implies extreme compositions. Possibly iron cores of destroyed larger planets or lava worlds with vaporized rock atmospheres. Surface temperatures exceed 2000 Kelvin. These worlds likely experience tidal disintegration, slowly being torn apart by intense gravitational forces. They represent planetary survival's extreme limit, worlds clinging to existence at the edge of obliteration. Even in extremity, planets endure. Free-floating planets, also called rogue planets, drift through galaxy unbound to any star. Ejected from star systems during formation or gravitational interactions, wandering interstellar space. Estimates suggest comparable numbers to stars, potentially 100+ billion in Milky Way. Some may retain internal heat, supporting subsurface oceans, despite lack of stellar warmth. Radioactive decay and residual formation heat could maintain liquid water layers beneath frozen surfaces. Life in darkness, sustained by planetary core heat alone. Nancy Grace Roman Telescope will discover many rogue planets via microlensing. Orphan worlds drifting between stars. Circumbinary planets orbit two stars simultaneously, like Tatooine in Star Wars. Kepler 16b, confirmed 2011, was first unambiguous detection. Approximately 10 to 15% of binary star systems may host planets in stable orbits. Beyond critical distance, where gravitational perturbations become chaotic, planets can maintain stable figure-8 or circumstellar orbits. Imagine standing on such a world, watching two suns rise and set, casting double shadows, providing light from multiple angles throughout the day. Science fiction becomes science fact. Twin stars nurturing worlds. The first confirmed exoplanets orbit not a normal star, but a pulsar. 1992. Alexander Volschan and Dale Frail detected 3 planets orbiting pulsar PSR B1257+12 via precise radio timing. Pulsars are stellar corpses, neutron stars left after supernova explosions. Volschan recalled, "When I saw timing variations, I initially thought instrumental error. Pulsars are clocks. They shouldn't vary." But pattern persisted. 2 planets, later confirmed 3, orbiting dead star. Planets likely formed from supernova debris or were captured. Extreme radiation environment precludes life. Even Death Stars host worlds. Geoffrey Marcy, prolific exoplanet hunter, reflected on systematic search efforts. Before 51 Peg, I'd been searching for years with nothing. After Mayer's announcement, I confirmed 51 Peg B within weeks using our Lick observatory data. It had been there all along, hiding in noise I hadn't recognized. Then floodgates opened. Dozens, hundreds, thousands of planets. We'd been blind to a universe full of worlds. Recognition requires knowing what to look for. Once the first exoplanet was confirmed, others emerged from data. The universe was waiting to be seen. Didier Queloz, co-discoverer of 51 Pegasi b, recalled scientific skepticism. After announcement, prominent scientists suggested we'd discovered pulsating star or stellar companion, not planet. They couldn't accept hot Jupiter. It violated their understanding of planetary formation. Took months of confirmations from other teams before community accepted we'd truly found new world. Taught me extraordinary claims require extraordinary evidence. Initial doubt transformed into acceptance as independent observations validated findings. Science self-corrects through verification. Truth emerges through persistent inquiry. Natalie Batalha, Kepler mission scientist, spoke of statistical revolution. Kepler didn't just find planets, it found the occurrence rate. We now know roughly 1 in 5 sun-like stars hosts Earth-sized planet in habitable zone. That's billions of potentially habitable worlds in our galaxy alone. This knowledge that we're not unique fundamentally changes how we think about life's prevalence. From philosophical speculation to statistical certainty. The question shifted from whether planets exist to how many and where. Abundance replaces scarcity in cosmic census. The habitable zone. Region around star where planet could maintain liquid water on surface. depends on stellar luminosity, atmospheric greenhouse effect, and planetary albedo. Sun's habitable zone extends approximately 0.9 to 1.7 astronomical units. Venus defines inner edge, Mars outer edge, Earth comfortably within. Brighter stars have wider habitable zones farther out. Dimmer red dwarf stars have narrow habitable zones close to star. Thick carbon dioxide atmosphere extends habitable zone outward through greenhouse warming. Complex interplay of factors determines habitability. Liquid water's delicate domain. Water vapor detected in atmospheres of multiple hot Jupiters, including HD 189733b and WASP 12b via transmission spectroscopy. Absorption features at 1.1 to 1.4 microns in infrared reveal water presence. Water presence common, but doesn't indicate habitability at 1000 plus Kelvin temperatures. Water exists as vapor in gas giant atmospheres at these extreme temperatures, not liquid oceans supporting life. But detections demonstrate our capability to identify specific molecules across light years. Same techniques will characterize temperate rocky planet atmospheres where water might exist as liquid. We learn by studying extremes. Potential biosignatures include atmospheric oxygen plus methane in disequilibrium. Both gases react quickly, requiring continuous replenishment to maintain presence. On Earth, photosynthesis produces oxygen. Biological processes produce methane. Phosphine potentially produced biologically. Dimethyl sulfide biological on Earth. No confirmed biosignature detections yet, but Webb and future telescopes targeting potentially habitable worlds. Sarah Seeger, MIT exoplanet atmosphere expert, explained, "We're designing missions to detect oxygen and methane together. Detecting both would suggest, not prove, but suggest, biological processes. We might find evidence of life within my career." The search intensifies. TRAPPIST-1 system provides unprecedented opportunity. 7 Earth-sized planets orbit ultra-cool dwarf star 40 light-years away. 3 planets, TRAPPIST-1, E, F, and G, in habitable zone. All transit allowing atmospheric studies. Michael Guillon, TRAPPIST principal investigator, reflected, "When we confirmed 7 planets around TRAPPIST-1, all Earth-sized, 3 potentially habitable, I realized we'd found best laboratory for comparative planetology humans will study for decades. 7 worlds, same star, different conditions. Natural experiment in habitability. This system will define astrobiology research for next generation." 7 siblings orbiting together. Tidal locking presents habitability concerns. Planets in habitable zones of red dwarfs, the most common stars, often tidally locked with permanent day and night sides. Extreme temperature contrasts between hemispheres. Thick atmospheres might redistribute heat, making planets habitable despite locked rotation. But locked rotation could concentrate water ice on frigid night side, leaving dayside desiccated. Habitability remains uncertain. Lisa Kaltenegger, Cornell astrobiology director, noted, "Most stars are red dwarfs, their habitable zones close, where planets likely tidally locked. Depends on atmospheres, magnetic fields, chemistry. TRAPPIST-1 will teach us. Questions awaiting answers." High-energy radiation from red dwarfs poses challenges. M-dwarf stars, 70% of Milky Way stars, frequently produce powerful flares. High-energy ultraviolet and X-ray radiation, potentially stripping planetary atmospheres, damaging surface chemistry. Prohibiting life as we know it. Planets with strong magnetic fields and thick atmospheres might withstand bombardment. Earth's magnetic field deflects solar wind, protecting atmosphere and surface. Exoplanets around active stars need similar protection. Whether red dwarf planets can maintain atmospheres remains open question. Shields against stellar fury. Future missions will revolutionize exoplanet science. Nancy Grace Roman Space Telescope, launching 2027, will discover thousands via gravitational microlensing and direct imaging. Complementing transit missions by finding planets at larger orbital distances, including free-floating planets unbound to stars. 2.4-meter mirror, same size as Hubble, with wide-field instruments optimized for survey speed. Roman will census planets throughout galaxy, providing statistical understanding of planetary populations. Cold planets, distant planets, orphan planets. Completing picture of planetary diversity. Expanding our cosmic cartography. Habitable Worlds Observatory. NASA concept planned for 2040s. Large space telescope, 6+ meters with coronagraph or star shade blocking starlight, enabling direct imaging and spectroscopy of Earth-like planets. Goal: detect atmospheric biosignatures like oxygen plus methane if present. Would represent humanity's first potential detection of life beyond Earth. Not seeing life directly, but seeing chemical evidence of biological processes. Oxygen and methane coexisting in planetary atmosphere, sustained against chemical reactions by continuous biological replenishment. This mission could answer humanity's oldest question. Are we alone? Deborah Fisher, Yale astronomer developing Express spectrograph, described technical challenges. Detecting Earth-mass planet in Earth-like orbit requires measuring stellar velocity to 10 centimeters per second precision. Human walking speed. We're pushing instruments to these limits. Express, espresso, future spectrographs will find true Earth analogs. Rocky planets, one-year orbits, temperate climates. Then we'll know if Earth is common or rare. Technology advances relentlessly toward Earth twin detection. Within decades, we'll know how typical our world truly is. Precision reveals truth. Breakthrough starshot concept proposes reaching Proxima Centauri in 20 years. Accelerating gram-scale probes to 20% light speed using ground-based laser array pushing light sails. could reach closest potentially habitable exoplanet in 1 generation. Conventional spacecraft require 70,000 plus years. Avi Loeb, Harvard astrophysicist, explained, "Engineering challenge is enormous, but physics allows it. Within century, we might fly by nearest exoplanet, sending back images. That will be humanity's first glimpse of another planetary system up close." From detection to visitation. Interstellar travel transitions from science fiction to engineering problem, reaching toward neighboring worlds. Sean Donegal Goldman, NASA astrobiologist, offered perspective on inevitable discovery. Question isn't if we'll find life signatures, but when. Universe contains trillions of planets. Even if life is rare, arising on 0.001% of potentially habitable worlds, that's still millions of inhabited planets in our galaxy. With Webb, Roman, future missions characterizing thousands of atmospheres, probability of detection increases annually. I believe within 50 years, we'll have strong evidence we're not alone. Patience and persistence. Search continues with improving tools. Discovery awaits. Consider the scale of planetary abundance. 5,600 confirmed planets as of 2026. Thousands more candidates awaiting validation. Estimated 100 to 200 billion planets in Milky Way galaxy. 20 to 50 billion potentially inhabitable zones. Each star you see likely hosts at least one world. When you look at night sky, you're seeing not isolated stars, but planetary systems, most with multiple planets, architectures unlike our solar system. A galaxy dense with worlds. Some planetary systems with hot Jupiters completing orbits in mere days. Others with multiple rocky worlds in habitable zones. Some with planets we can barely imagine. Lava worlds with molten surfaces. Water worlds with global oceans hundreds of kilometers deep. Carbon planets where diamond forms instead of silicate rock. Rogue planets drifting between stars. Circumbinary worlds orbiting twin suns. Super-Earths with crushing gravity. Mini-Neptunes with thick hydrogen atmospheres. Diversity beyond expectation. We live in populated galaxy. Planets surround us, separated by light years, but present nonetheless. Cosmic loneliness replaced by cosmic community. We just haven't met neighbors yet. Statistical probability suggests life exists elsewhere. We don't know where. Don't know when we'll find it. But mathematical certainty replaces philosophical speculation. 1 in 5 sun-like stars hosts Earth-sized planet in habitable zone. Billions of potentially habitable worlds. If life arises on 1% of habitable worlds, that's 200 million inhabited planets in galaxy. If life arises on 0.01%, still 2 million inhabited planets. Even conservative estimates suggest abundance. We're not unique, not isolated. We inhabit galaxy teeming with worlds, some barren, some with simple chemistry, some perhaps with complex life. Maybe somewhere someone looks up at their sky wondering if they're alone. They're not. We're here. The Drake equation, formulated 1961 by Frank Drake. Estimating communicative civilizations in galaxy. Initially, most terms unknown. Now we know practically every star has planets. 20% have potentially habitable planets. Remaining unknowns: how often does life arise? How often does intelligence evolve? How long do civilizations persist? We've narrowed uncertainties dramatically. Some answers known, others await discovery. We can't physically visit distant exoplanets with current technology. Proxima Centauri b, at 4.24 light-years, requires 70,000 years with conventional spacecraft. But laser-pushed light sails might reach it in 20 years. Gram-scale probes sending back flyby images. First credible interstellar mission concept. Within century, humanity might glimpse another planetary system close up. From detection to photography, patient progress across impossible distances. Tonight, when you look at stars, remember, each likely hosts worlds, planets orbiting in darkness and light. Some frozen, some scorching, some perhaps temperate with liquid water. We're searching with improving tools, Webb characterizing atmospheres, Roman finding thousands more. Future telescopes seeking biosignatures. Each observation brings us closer. Each spectrum reveals composition. Each transit confirms another world. "5,600 confirmed. Thousands more candidates. Billions in galaxy. Trillions in universe. Most stars have worlds. Many worlds potentially habitable. Some perhaps inhabited. We're searching. We're learning. We're patient. Floating among stars, knowing most harbor planets. Contemplating cosmic community. Not alone. Never alone. Just haven't confirmed neighbors yet. Breathing with shared cosmic heritage. Carbon in bodies forged in stars. Water in cells delivered by asteroids. Made of universe. As any life elsewhere would be. Same elements. Same physics. same chemistry. Perhaps different forms, but sharing fundamental building blocks. Universal kinship, cosmic connection, shared origin. For now, we search. We wait. We keep patient vigil, knowing discovery is matter of time. Not if, but when. Telescopes pointed skyward, instruments measuring precisely, algorithms searching data. Silence between observations filled with potential. Each photon arrival carrying information. Light from distant worlds, filtered through alien atmospheres, bearing chemical signatures. We decode the messages, reading cosmic letters, translating starlight into knowledge. Thousands of distant worlds orbiting stars too faint to see, but present nonetheless. Circling their suns, maintaining orbits, perhaps harboring life. Unseen but real, distant but existing, unknown but knowable. Statistical certainty replaces uncertainty. Billions of planets confirmed by mathematics. If not in this system, then in next. If not around this star, then another. Abundance guarantees presence. We inhabit populated cosmos, member of vast community. One world among countless. Breathing slows to match patient observation. Inhale, cosmic perspective. Exhale, isolation. We're part of something vast, connected to all worlds. Planetary kinship, shared existence, universal belonging. Your breath joining rhythm of cosmic time. Planets orbiting, stars burning, galaxies rotating, all moving together. You're part of dance, breathing with universe, existing among worlds. Rest now, knowing you're not alone, surrounded by worlds. Most invisible, some detectable, all real. cosmic community embraces you. Billions of planets, countless possibilities. Let this knowledge bring peace. We're part of abundant universe, not isolated oddity, but member of vast family, worlds beyond counting. Sleep surrounded by planets, dream of distant places, rest among cosmic neighbors. $5,600 confirmed worlds watching over your sleep. Billions more waiting discovery. Each a place, each a world, each existing. You rest among them, breathing peacefully, drifting gently. The search continues while you sleep. Telescopes observing, spectrographs measuring, computers calculating, discovery approaching. But tonight, you rest. Peaceful sleep, surrounded by worlds. Let thoughts dissolve like stars at dawn, fade into peaceful darkness. No need to search, no need to wonder, just rest, floating among planets, drifting through cosmos, breathing slowly. Your consciousness expands to embrace cosmic scale, then gently releases. Too vast to hold, perfect to release. Let go. Float free. Rest deep. Sleep sound. Billions of worlds orbiting in darkness. You among them. Resting. Peaceful. Safe. Surrounded by cosmos. Embraced by universe. Home among stars. Each breath slower than last. Each thought quieter, fading gently, releasing softly, drifting peacefully into sleep, into rest, into dreams. Distant planets orbit unseen. You orbit into sleep. Natural motion. Gentle transition. Peaceful journey. From waking to dreaming to deep rest. 5,600 confirmed. Billions unconfirmed. All existing. All orbiting. All there. As you're here. Existing. Resting. Cosmic community holds space for your rest. Planets circle their stars. You circle into sleep. Natural rhythm. Universal pattern. Rest joins cosmic motion. Sleep becomes orbit. Dreams become journey. Let go of searching. Release wondering. Tonight, just rest. Among worlds. Within cosmos. Peaceful sleep. Deep rest. Complete release. Stars watch over sleeping Earth. Planets orbit unseen. You rest among it all. Part of everything. Connected to cosmos. Sleep now. Rest deep. Dream gently. Breathing so slow, heart rate peaceful, body still, mind quiet, spirit at rest, among worlds, within universe, at home. Your breathing slows naturally. 4 counts in, 6 counts out. Rhythm matching cosmic patience. Stillness within. Tomorrow night returns. Stars waiting. Patterns persist. For now, peaceful rest under For now, peaceful rest under ancient starlight. The universe continues. You rest within it. Returning always, patient cycles. Peaceful darkness, rest. Breathing slowly, drifting. Rest now, sleep. Peaceful, drifting.
sleep, rest. Quiet, peace, well, reporting. Sleep.